So we want ZK to be quick, right? But so what does that mean? When you say you want something to be fast, you wonder, like, for whom and to do what? So there's a couple of different options that might be available for this. A lot of people have spent a lot of time doing research, and extremely excellent research, on trying to make sure that clients can generate proofs efficiently. There's some really wonderful work on that subject. But also, like, we want to make sure that nodes can verify proofs efficiently. We want to make sure that nodes can produce updated state that can be made use of quickly. And we want to make sure that clients can consume updated state quickly. Like, there's an entire pipeline and network of things that need to happen in order for a fully integrated ZK system to be efficient for all people who participate in it. So what we observed in Penumbra is that for a ZK blockchain like ourselves, most users spend most of their time doing things other than generating proofs. So if that's the case, what are they doing? So I want to take a second and walk through what happens in the entire architecture of Penumbra and focus on what it is that we're spending the most time doing in most use cases. So this is what it looks like conceptually. We've broken down the client and the full node. So Penumbra, to take a step back, Penumbra, from the get-go, we wanted to make sure that we designed things in a way that we prioritized clients as full first-class citizens of our ecosystem. We wanted to make sure that we can run in restricted computing environments, like processors that are not as fast as a big desktop or a chunky server, like maybe mobile phones or a browser extension in WASM or things like that. We've broken out our client into a couple of different pieces. We've got the custody service, which has a particular interface that it talks to the wallet logic over. That interface means that we can swap out different kinds of custody. We've got a view service, which has only the capability of viewing your transactions and not making transactions on your behalf. And that tells the wallet logic in clear text what things you're actually able to do. And the only interface between the client and the rest of the network is that it receives viewing information in encrypted form from the Penumbra daemon, and then it transmits transactions back to the network by broadcasting them directly to Tendermint, which we use as our consensus engine. And Tendermint is speaking to the rest of the network, all the Tendermints having a group conversation. So most of the time, when you're sitting and you're doing things, you're not actually spending most of your computational effort on constructing transactions if you are a normal user. There are some like outlying use cases where like you might be doing quite a lot of like really rapid transaction making if you're like doing specialized trading bots and things like that. But most users aren't going to be doing this. Most users are going to be doing this quite a lot. They're going to be downloading the history of the chain, and they're going to be trying to synchronize it with their state. So sync is something that's really, really important to get right and get fast. In particular, unlike a transparent blockchain, you can't just query the chain to find out what's going on. So like every client has to maintain their own copy of private state that's relevant to them so that they can generate proofs. And those proofs have to be generated based on their fragment of private state. So this view service needs to be quite efficient. So the status quo is that we use Poseidon hash, which is a snark-friendly hash that I suspect many of you have heard of. Poseidon is really great. It's very friendly for making efficient snark proofs, but it's slow in software. It's 100 to 1,000 times slower than doing very efficient cryptographic hashes that don't have to support snarks. In a traditional Merkle tree design, we have to insert every commitment into the tree sequentially, because if you skip any, then your root hash is going to be different. So you can't parallelize, and you can't accelerate by summarizing the number of updates that you have to do. Additionally, when you make an insertion, you have to compute many hashes. You have to compute all of the hashes all the way down from the point at which you insert the leaf of your tree all the way back up to the root every time that you insert. And of course, if you have a fully integrated ZK8 system like this, when the client is synchronizing, you don't want to lose all of your progress if they Control-C or if the computer crashes or any of this. So you want to be repeatedly checkpointing your state. And if you don't have a tree that supports serializing it efficiently, then you're repeatedly persisting the entire state over and over again as one giant blob. So this is not great. And in particular, this status quo punishes users when the network succeeds, which is sort of the opposite of what we'd actually like to be the case. We'd like to reward users for the network actually being successful. So why is this true? Well, so as the number of transactions increases, then proportionately to that, the amount of hashing effort that any client has to do increases. Not proportionate to your own effort, but proportionate to the amount of transactions that are globally happening on the network, because you need to process everyone's commitments that have ever happened. I argue that like the state of affairs that should exist is that the effort that you spend on synchronizing your state should scale roughly with only the amount of activity that you yourself are performing. It should not matter how much everyone else is doing. It should only matter, basically, how much you are doing. So how could things be instead? Well, the Poseidon hash is, as I said, snark-friendly but slow in software. So we use a wider rate, rate 4 for the Poseidon function, to make the tree wider and shorter. So that means that we're doing less hashing all the way down. Originally, in a conventional Merkle tree design, we have to insert every commitment sequentially. So instead, we came up with a tree design that lets us skip most of the commitments and construct subtrees in parallel rather than sequentially. This problem of having to compute many hashes every time you do an insertion led us naturally to design the tree to have a lazy frontier, which avoids most of the work on every insertion so that you only compute the frontier when you actually need to calculate the root of the tree. And then, of course, we have to persist that updated state. So instead of persisting the entire tree every single time that we want to checkpoint to disk, we just serialize an incremental slice that represents everything that's changed since the last checkpoint. So this design that I've outlined the conceptual properties of, we call the tiered commitment tree. And instead of giving you a lot more bullet points about how it works, I want to give you a live demonstration so that you can visualize what it looks like inside my head. Like when I was thinking about constructing this talk, I wanted to give you an intuition for what it feels like to see this work. Because when I was designing this tree, I had all these pictures, I had all these shapes rotating around in my brain. And I wanted to show you the shape rotation so that you can actually understand what's up. So let's zoom in and see what's up. This is a commitment, a note commitment here. And this is its hash above it. So I can insert, as I'm inserting these things, I'm inserting some of them by remembering what they are, and I'm inserting some of them by just remembering their hash. As you can see, if I don't remember things, then they just get summarized because this is a sparse tree after all. But I always preserve the things that are remembered. And let me just insert a bunch more. You can see we have this sparse tree structure here. Now, if I make a spend, then I'm never going to need to prove anything more about that commitment. So I can just forget about it like that. And then we get some more abbreviation like this, etc. So you can see that this is a fragment down here that we're viewing of what the authentication path is down to, for example, this commitment, which is the 1226th commitment of the 0th block of the 0th epoch. And so you can read all of these numbers as being epoch/block/commitment within that block. So I said this data structure is called the tiered commitment tree, and that's because we represent it as a 3-tiered structure where we have blocks within epochs within the global tree. So let's zoom out a little bit and say this is the end of the block. We've inserted all of the commitments that are relevant to this block. So we start a new block, and we start inserting some commitments like this, and like that. And so we're going along, and we don't see any commitments that are relevant to us. So we've gotten to the end of this block, and then we finish the block. And so the entire block becomes summarized by a root hash, because the tree, after all, is sparse. So why did we have to do all of that work, right? Why did we have to insert all of these commitments only to summarize it by the root hash? Well, this seems like we've done more work than we actually needed to. And in fact, we have. So the Penumbra architecture commits the intermediate root hash of every block into our public Merkle tree, the jellyfish Merkle tree, borrowed from the DM blockchain. And so what that means is that client synchronization can just stream the root hashes of each block, provided that you don't actually need to know what any of the commitments are. You can just insert the root hashes of each block. And that means that you can accelerate by performing only one hash per block instead of performing 1,226 hashes. This is, very advantageous. You'll notice that here there are some little dots that represent the parts of the tree that never ever got filled in. We use a placeholder padding because every node has exactly 4 children. So zooming out a little bit more, you can see that this is actually just the first epoch of many. So we can finish the epoch and then start a new one. So we're doing some work in the epoch, and maybe we don't have any commitments in these blocks. And say that we didn't have any commitments there either, so we just summarized a lot of blocks, right? Can't we just apply the exact same logic again? And in fact, we can apply the exact same logic again. So let's just summarize the epochs instead of working on building them directly. So we can just do this instead, streaming each epoch root and doing one insertion per epoch. And if our epochs are, multiple days in length, then this means that you do maybe a few hashes, like under 100 hashes, in order to construct the local copy of your state for an entire year of chain activity. And this is where the claim of 4 million times faster than the naive way of doing it comes from. If you really filled up the tree, if you had completely full blocks and completely full epochs, then you'd be about 2 to the 32 faster doing it this way than doing it naively. I think that's a pretty reasonable speed up. I'm relatively happy with that. So you might be wondering, why is the frontier pink? And that's actually a very deliberate part of this visualization. It's because the frontier, we haven't actually computed the hashes of the frontier. But let's say that we want to witness the root of the frontier. Well, we need to compute the authentication path all the way up to be able to know what this root hash is. But if we were doing this every time, then we would be doing a lot of repeated work. So instead, we just don't do it until we actually ask for what that root is. Another point that I wanted to make is, as I was saying before, we do incremental serialization. So as you can see here, suppose that we're at this point, and I put a commitment there, and I insert 1,000 more things. So you'll see that the part to the left of what I just did, this part is basically unchanged. All of the hashes haven't changed because the only things that change are the things on the frontier, which we don't compute until we're ready to compute them, and the things that we add anew. So what that means is that if we can serialize incrementally only the things that have been added, then we can persist things using the actual minimum amount of writes to disk. So this reduced write amplification in our testnets by about 100 times factor when we implemented this. So about now, the way that the current status quo is that we're synchronizing on our testnets at about 10,000 blocks per second on this MacBook Air. And that's only taking advantage of sequential computation that abbreviates blocks into their block hashes, not taking advantage of epoch acceleration, not doing any parallel acceleration. And in the future, we're going to be integrating fuzzy message detection, which will mean that instead of streaming and trial decrypting everything in order to do this, now trial decryption is much, much cheaper than doing hash computation, but it still costs something to download things from the network. We have this fuzzy message detection capability that we're going to use to delegate the scanning of your relevant commitments to a third party who can only give you like a probabilistic ZK Bloom filter over what things you've got to detect. And then you can only stream those bits and construct your tree. So we estimate that you should be able to just like synchronize like that once we've implemented all of that. So we don't anticipate that the FMD capability is going to be ready as of when we launch the mainnet, but that's an upgrade that we can perform after the fact because all of the cryptography is already there. So we've got orders of magnitude to get better than 10,000 blocks a second. You know, I had some backup slides here in case the live demo didn't work, so I'm just going to real quickly zoom through those. Here's a nice visualization of what I mean by the incremental insertion. Like the difference between this and this is just this. So we only serialize this. I want to change tracks real quickly and note that this is extremely fast, right? You know, 10,000 blocks a second is pretty reasonable. When we go to mainnet, which is going to be soon, TM, this tree had better be correct, right? Because it's not like we can do a database migration after the fact because everybody's state is you know, shielded and private, and so it would be really difficult to actually change the way that this data structure works after we deploy. We want to be really sure that things are actually implemented well and perfectly correctly as best as we can assure. We really like types at Penumbra. We're building everything in Rust. And so the way that this tree is constructed is using types to really guide the tree to be constructed as perfectly as possible without having to write tests. Our type system prevents us from constructing any invalid trees whatsoever. So just sort of dropping into Rust lingo a little bit, we use recursively defined traits or like inductively defined traits on nested generic types to write these structure-preserving traversals over precisely shaped trees. So what that just means is that we've written down some very precise types that say the tree is exactly this tall and there are no dangling paths and the frontier is exactly this kind of shape and the complete part of the tree is exactly this kind of shape, so that it's impossible to even compile an implementation of this tree that doesn't actually match the structure that we want it to have. And then the only bugs that we can really have that are left, you know, knock on wood, are bugs related to computing the hashes themselves, which are pretty easy to test. So here's an example of what I mean by using these really precise types. I have this little comment here. We have these nested generic types that say a tree, an individual tier is exactly eight nodes deep, followed by a leaf. So you can't have anything that's the wrong depth. And this actually gives us an efficiency boost at runtime because you don't have to branch on whether you're at the bottom or not. And then we enumerate all of the possible patterns of children that you can have of a leaf. And if you notice, you'll see that there's no possibility that you can have a node that doesn't have children. Because if you don't have children, then you should be folded into the node above you and summarized. So you don't have any dangling branches, and that's preserved by the property of how the tree is structured. So I want to say, you know, thanks for paying attention to this little demo. But before we get to questions, I want to invite you to play with this yourself while we're doing questions, if there's question time. So I actually am hosting this live at nct.penumbra.zone. And if you go here, we've got this live tree that you can play with on this screen because this is reflecting everything that everyone is doing right now. And with that, I'm happy to go to questions. Yes, so it's nct.penumbra.zone. Yes?
Can you just try the TLDR, the way that you're minimizing the root construction, in which ways is that different from like just the Merkle mapping range? Like the way the NutriXO does it?
I'm not familiar with that work, but I would be fascinated to hear about it.
Maybe we can talk afterwards.
I'd love to, yeah.
And just a quick announcement for everyone. When we ask questions, we've got a mic here. Please use the mic. It's a recording. You won't understand.
Yeah, and I'll try to repeat the question if anyone asks.
Yeah, we've got a mic.
Okay, great. See, hands off the computer. Someone's doing it.
Does anyone have any more questions?
Maybe it's more on the, is this working?
Yep.
Maybe it's more on the implementation, but you showed some of the Rust code that you have and it looks quite complex. Like, do you have an approach to simplify that with macros or something like that?
The Rust code that I showed you is some of the more complex parts of it. Like we define, there's this one module that defines like what's the structure of a node, and there's this one other module that has this like deeply nested type. You could write a procedural macro to generate this stuff, but I'm not sure that you would actually save on lines of code written. Because you'd have written the procedural macro, and the length of that would be basically as long as the code that you've written there. And I'm not sure that it would actually clarify the code. It is something that I thought about. And I think that if we were to generalize this to a use case other than our own, we'd really want to do that. Because then you'd want to be able to say, like, how many tiers do you want? And how tall is each tier, et cetera. And so, it would be entirely possible to do this. It's just that it wasn't the right cost-benefit trade-off for us at the moment.
Check. Okay. So you demoed some type-level programming. I'm not actually familiar with what it means to define a trait recursively, but there's sort of a wave of blog posts I've seen in the last 2 years or so about type-level programming that you can do in Rust. It's made possible by largely generic associated types. I'm curious what previous experience you guys brought to bear on type-level programming, since it seems like a fairly new trend in Rust, and then also, are you using this generally for any data structures that you define, or is it used more pervasively across your code base, and sort of what's the design decision there?
Okay, there's a couple of embedded questions there, and I'm going to go in reverse order. One of the things that is a challenge for us to figure out that we've been trying to fine tune as we're building this thing, we want the thing to be real, and we want it to be real as soon as possible. So that means that we want to rapidly prototype stuff. And sometimes when you use too many types, what that does is it just like pours epoxy over the entire structure of your code, and then you can't really rapidly iterate because everything is like frozen in place, and you have to just like smash it to bits and try all over again. So we sort of take this balanced approach between like, do we want to like really nail down this design and get it perfectly right in this exact place, which for the Merkle tree design is absolutely what we need. But for other places in the code, we're a little bit more lax, and then we sort of are going to take an iterative approach to freeze things and make them be more well-typed and more better encoded, etc. You had another question that was before that, and that was about like what kinds of type-level programming we're using. So this doesn't use generic associated types. We're using the stable Rust compiler. And the only real trick here is that if you have a nested generic type, so like I was showing you with the like node of node of node of node of leaf, instead of defining something as a recursive type, you define it as a nested generic type where the recursive parameter of the generic parameter of the generic type represents the points of recursion. And then you can write a trait where the trait depends on the trait itself being implemented for the type parameter. And that allows you to have an implementation that does like static dispatch all the way down to the leaf. And so you get this like inductive function that's defined over this precisely shaped structure.
And we got time for probably one more question.
I guess that's a really easy one. How is the source open code? The other way around, is the code open source? That's what I'm trying to ask.
The code is open source. Everything we do at Penumbra is completely open source. So you can go to github.com/Penumbra, and this is in the Penumbra /Penumbra monorepo under the TCT, Tiered Commitment Tree directory. And I would love to hear any of your comments. Please email me.
Thank you very much.
And thank you.